Oops. So I think we were looking at symbols of the tray, right? Yeah, we talked about these, right? These you're probably familiar with, huh? It works a lot better if I hook it up. It is on though, right? So what we have, what's this guy? DC power source. This is a what? AC. This is a resistor, right? This is a connection. This is something called an inductor. It's a coil. It's also called a coil. Also called a choke, by the way. This is a capacitor. This is a transformer. Single pole double throw switch. Ground. Fuse. These are some of the symbols we're going to get into in motor controls. I was going to kind of hook this basic circuit up, but I ran out of time. I'm starting it over here. So this is our power. Some people call them power rails. Generically, we call them L1 and L2. We consider L2 to be the common, right? Okay. This is a symbol for we've already talked about these guys. Well, what type of pushing? Momentary contact. Momentary contact, which means what? Yeah, it's a push and release. Normally closed push button. And then you see for normally closed push button. So what is this? This is normally open. Well, actually, it's a. It has two ways to connect it. Anytime you see these clear dots like this, they're supposed to be clear. This indicates we have a connection. This indicates a terminal, contact to, right? Terminal means something that we can connect to. Conductors, what's the function of the conductor? Why is the conductor in the circuit? To get the power from the source to the load. It's got one function in life, is to get the power from the what? From the source to the load. So eventually every conductor is going to come to an end. The technique of bringing a conductor to an end we call termination. Where we make the connection to are called terminals. So anytime you see that clear dot, it means that's a terminal, right? Which means that's where we would connect to this device. This could become with compression. Most of the time it could be done with screws. Most of the time in industry we use screws. We're going to use banana plug jumpers, but the actual device itself has screws on it. And then of course we use what we call banana plug. You know what banana plug is? Everybody okay? Okay. So we call a banana plug jumper. I'm gonna get one. That's not so these are called banana plugs. This would be the male, of course. So what we have on our devices is we have the female. And so what we can do with banana plugs, we used to teach them, and you can see some of these units around like this. This is what we used to teach motor control. So this was our push button station. Now we learned real quick that some people know how to use a screwdriver and some people what? You know, some people think, by God, you got to tighten this thing down until the person next to you can't tighten it down anymore. And then they get these electric screwdrivers on there, and they don't get them in there perfect, and they slip and they strip the things out. So we decided to go a different route, where we make our connection using banana plugs, and that way we've been using these same trainers for eons, guys, a long, long time. But this is the way we originally taught it. As soon as I get my camera. And so what? These guys was getting tore up all the time, because they actually made the connection to all the devices using these screw terminals right here. And of course, there's one missing out of here already, and the screws would get lost. So that's why we decided to go to these banana plugs. This company was in Birmingham, IMCO. They were in Birmingham, and they designed these trainers for us. And then they sold the copyright to ECI, which is what you got there, and they put out basically the same trainers. But we actually designed them. We don't get credit for it, but we designed them. But now they're on blue backs like that if you order from ECI. So when we make these connections, so every one of these little dots is a connection point. We call them terminals, where we're going to connect one of our conductors to that, right? That makes sense? This round circle is a symbol for what? This guy right here. No. Yeah, this is a relay coil. Y'all understand that, right? So it works on the principle of a solenoid, but it's got contacts on it. I showed y'all a solenoid last class. But when the solenoid engages, it shifts that armature or that plunger and either opens contacts or closes contacts. Now what we do in that symbol, now normally these names don't fit inside the coil. So if I was to show you a true diagram that was given to us, this is actually a line section that was out in USD, of course. So what we have. So these are the coils, and see, they give the coils name. So since the name don't fit, so this coil right here is called 5B1DB. And so since it don't fit inside the coil, it's going to be up above it, right? You understand that? And so all these coils are going to have names. Are you okay? So here, since we're basically teaching this, they're calling this coil, they're calling it M. Now, why do we need to name the coil? So we can indicate what contacts are being controlled by that coil. So the way this works is the contacts have the same name. So notice they're calling this relay what? M. And then down here I have a what? M. And then right here I have an M. So, I mean, those contacts are being controlled by that relay coil. So this is a symbol for a what? A normally closed contact. And this is a symbol for a normally open. So what happens, the way this thing works is how? I come over here, so right now the way it's set, and this is normally contact or closed. So I have power sitting right here, right? You understand? And then I have power sitting right here. So I need to energize that coil, so I've got to get power to the what? To the coil. What do? Press that button. As soon as I press this button called start, this comes over. It's a momentary contact. So as soon as I press it, what do? Yeah, but what happens is when this energizes, right, what happens? This contact down here does what? This one closes, right? You understand that? So now I got a secondary path. Now I can do what? Now I can let go of the start button. And this guy is sealed in. We call that a memory circuit. Some people call it a 3-wire circuit. Some people call it a seal-in circuit. So what I did is I hit it, and then I can do what? I can let it go. Now what happens is now, so originally this light down here, this is a symbol of a what? Light, yeah. Electricians call them luminaries. And so it starts off, before I press that button, this guy is on, and as soon as I press it, this thing right here will do what? Open, and the light will go. Now this is the diagrams we're going to wire by, and these are called what? Ladder ground. Some people call them line diagrams. So in programmable controllers, the main language we program in programmable controllers is called ladder logic. So that means you write a program with this. Of course, here we're going to be hardwiring circuits. In PLCs, we program most of the circuit into the computer, and then we output to big relays. Are we okay? Make sense? Now what these are called overloads. So in motor controls, this is the symbol of a motor. We have a circle, and we bring the wires in from the top. This would be a single phase, some type of single phase motor. And then if I come in with 3 wires, this would be a what? This would be what we call a 3-phase motor. And those are the 2 types of AC motors we got, and DC motors are a little different. So later on we'll learn a little bit about motors. The problem with motors is that anything that's at rest wants to do what? Stay at rest. Anything that's in motion wants to stay in motion. The only thing that makes them stop is something called friction, and everything's got some type of friction in it, right? So when does the motor need the most current? While it's running or when it's starting? When it's starting. We call it start current. That start current could be, and it's also stall current. They also call it lock rotor current, which means if you was to lock the rotor on the motor and put power on it, it would pull start current. But if I leave that start current on that motor, the motor's going to burn up because it's not designed to handle that start current for a long amount of time, right? You understand? So what happens is that we got these devices called overcurrent protection devices, and normally we come up here and we use fuses. Oh, that's not a symbol for a fuse, guys. That's a symbol for an overload. So up here somewhere, we might have a big old disconnect where we can disconnect power from the system. And somewhere up the line, we're probably going to have a fuse. Industry still uses a lot of fuses, and why is that? Yeah, they're cheap. Now the problem is these fuses have to allow the motor to start. So if they don't allow enough current for the motor to start, then they would blow, right? So this is a big problem we have with motors. Your fuses or your overcurrent protection devices have to let the start current come through. So what happens if the motor stalls? The fuses won't blow, because they're rated between 120 and 120 to 150% of the start current, not the run current. So what that means, we need to come up with some method where we can sense when the motor draws more over current over a certain amount of time, right? You understand? So this is what we call overloads. And these are symbols for overload sensors. So what we do is we put overflow sensors out in series with the motor. So everything that goes through the motor has to go through the sensor. So what happens is that if the motor stalls, these overload sensors will sense over current, but over time. Y'all understand what it means? So they will let the start current come through and allow the motor to start. But if the motor don't start, or if it stalls, then these guys are going to sense that. And what it does, it opens one of these contacts right here. So this would be three-phase. If it opens one of these contacts, then what's going to happen to the relay? It's going to drop out, right? Or it's going to de-energize. So that's what those symbols are for there. These are overload relay contacts. This is the symbol for the sensor that's in the series with the motor. And then it kicks out the motor if what? If it stalls or if it won't start. So that's what these symbols are right here. Notice, and that's the only thing that's allowed on the L2 side is overload contacts. Normally our load connects directly to L2. So you can tell right off the bat if it's a motor starter relay because it's going to have what? Overload contacts on the L2 side. Huh? If they're wired correctly. Some electrician could wire them anywhere in this series string. So they could wire their overloads over here, but that wouldn't be according to industry standard, right? I understand that. So the only thing allowed between the load and L2 is overload contacts. So everything else, L2 connects directly to the L2. The relay coil connects directly to L2. Or the light bulb connects directly to L2. Now we're going to keep adding symbols to this, especially control devices. So control devices, we're pretty familiar with switches, right? So you use those to control your house all the time. Everything you got some type of switch on it, so you can do what? Turn off, or put it in standby. Just about all your electronic devices now are never really turned off unless power fails. They're in a standby. So they got a little push button on them. They don't have a nice little switch. They got a little tap you can push to turn them on, right? And that's why your TV will remember the channel you were on, right? Your cable box will remember what channel you was on. So most of our stuff is. But we have other types of sensors. These are just a few. So a sensor, we defined a sensor. What does a sensor do for us? So we're going to have a section of lecture on sensors. So what does a sensor do? What does your senses do? You have sensors all over.
Use the signal to the
so it takes a physical stimulus and converts it over to an equivalent electrical signal so your brain can process. So your brain does not know what smell is, your brain don't know what hearing is, your brain don't know what seeing is. All it understands is how to interpret electrical signals. And it's amazing, isn't it? So that's what a sensor does. So these are basic digital sensors. These are basically mechanical sensors. And we'll look at some solid state sensors later on when we get in there. But this guy is what? This is the first one. What's this? Float switch. Y'all understand what a float switch is, right? So if you got a house that's got a basement in it, it might have a sump pump in there. It don't run all the time. When does it run? When you get water in the sump, right? You understand that? So when the water comes up, on this one, this would be normally closed, so this one will run all the time, right? You understand that? So we have to have it normally open. This is a float switch. This is a what? That pressure switch. This is a flow switch. And this is a timer. We'll look at timers later on. So relay contacts are drawn with these two symbols right here. So this guy right here, and this guy right here, these are one without the angle line through it is a normally open contact, which is being controlled by a relay, right? You understand that? And then the one with the line through it, this is a normally closed contact. So the normally closed contact, when the relay is de-energized, it's going to be closed. The normally open contact will be open, right? And then when we energize the relay, then they're going to swap. We okay? I think I passed that one of those relays around that had all the control. So this is a typical line diagram or ladder diagram. So the way it goes, this is L2. I'm sorry. This is L1. This is L2. Now, what goes between L1 and the load? Well, this is where you're going to put all your control devices out there. Those determine when the rung is either true or false. So when we say the rung is true, then this is when we're going to get power over to our load. If the rung is false, that means we're not getting power to our load. So control devices go between what? L1 and the load. Then our loads go between between the control devices and L2. Now we know these control motors because they're overloaded. Are we okay? That make sense? Yeah or nay? These are relays. What's the symbol for? Lightning. And you see why we call it a ladder diagram, because it's got a similar to a what? A ladder. So each one of these circuits that runs from L1 to L2, so here's a circuit right here. We refer to this as a rung. Are we okay? So notice all these different circuits. So this would be a circuit. Right here. Everybody okay? That makes sense? Any questions? This is a residential wiring diagram for electrician. So we teach a class here called blueprint reading. What usually happens, especially if you're in the electrical trade, is that plumbing has to go a certain route, air conditioning has to go a certain route. So things inside a building have to go a certain route. Wires don't have to go in a certain route, right? You just got to get back from your load out to your panel box. So this is what they do for the electricians. They'll just come up here and put these arrows right here. And what does that mean? That means it goes back to the panel box. It's up to you to figure out how it gets there, right? These are duplex connectors. These are lights. Light still has the same symbol. Panel box is a different kind of panel box. So here's the panel box right here. Here's the panel box right here. So this is the diagram that the electrician would have to follow. They just don't show the wires. They just point them out and put an arrow on it, and the electrician knows to get it back there. This is an electronic schematic. So first of all, one thing you got to do, anytime you get into these drawings, you got to learn the symbols of the trade, right? Understand? Because these diagrams are not going to be drawn with pictures. We call those pictorial drawings. Usually when you go out and buy a new TV, it comes with a pictorial drawing, which means they'll have a picture of a TV, they'll have a drawing of a VCR, they'll have a drawing of that, because this is going into people's hands that don't understand symbols. When you get into the trade, every diagram you have is going to be with a symbol. So that means even carpenters, when they look at floor plans, those are nothing but a bunch of what? Symbols, right? You understand? That they have to interpret. So they don't draw the house, they draw the symbols of the house, right? You understand that? So this is electronics. That's an operational amplifier. In fact, this is a power amplifier. So what we got to do, of course, is we got to learn symbols. Learn the following symbols located in the textbook appendix. So you need to make a note of these because we're going to be using these symbols all the time. So in the appendix, this book is really good. It covers symbols of just about all the electrical trades. So push button, single circuit, double circuit. So what I showed you a while ago was the double circuit push button. selector switches. Go ahead. Okay. By the way, this is up on Blackboard. Y'all got access to Blackboard? Just go into course content. Go to what? Chapter or intro to electricity. We're not even in the book yet. This is not chapter 1. So this will be electricity, intro to electricity. Then there's something called slides or PowerPoints.
Symbols are in chapter 2 in the book.
No, but in the back, there's appendix back there, and they got all type of symbols there. So basically, the book kind of goes, adds on and adds on and adds on to the symbols we already know. Understand that? Aren't there a bunch of them back here? Yeah. Yeah, I thought when you said $54, I forgot there's a workbook for this. And we don't require the workbook anymore, but it's good. It's a good study guide.
So which book do we get?
You got 2 books to get. You got the lab book, right, and you got the textbook. No, he said he found it online for $54, but it was paperback. But it's a workbook that goes with that, and we don't require y'all buy that anymore.
No, Amazon work rental is $10.
So how much does the textbook cost?
You said you can rent it for $37, but
I did it today. I did it from Amazon today.
Oh, you bought it today?
Rent.
You can rent from Amazon?
Yeah,
Wow!
and it's cheaper than checks.
Amazon's coming up.
I didn't know. I honestly did not know you could rent from Amazon.
I read my scholarship book on Amazon.
Yeah. Even your digital book last time I took it with you, Mr. Lee, that rent that book from Amazon.
So here in course content, right? And basic electricity is what we're working in now. And then here's the lecture slides. So this is exactly what I've got, right? Everybody okay? Except they're not animated. So selector switches, coils, of course we already know that. Pilot lights, transformers, we're okay that, right? Push button, single, and double circuit. So a single would be, so this would be a double circuit right here. You know, see why? Because I got a terminal, I could bring another circuit in right there, right? You understand that? So this would be a double circuit push button because I have terminals at the top. So a standard normally open push button would look like this. But see, they got that other setup here, which means I could use this as a normally closed, or I could use it as a normally open. Normally we don't use it for both. That makes sense? Mm-hmm. And we do have some of these push buttons over there, by the way, on one of our push button panels. It's very important to learn the symbols used in the reference drawing of your chosen trade. It is also just as important to learn the terms used in the language of your chosen trade. So this is going to be a terminology class, and also we're going to learn symbols as we go along. Are we okay? Everybody okay with volts, amps, and resistance? Now we're going to have to learn a little about this. In your AC, you're going to learn a lot about reactance when you take AC. We're going to learn just enough to understand what's going on. So resistance and reactance are a measure of the amount of opposition to the flow of current. the unit of opposition is called the ohm. So no matter what type of opposition an electrical circuit you have, it's measured in ohms. That makes sense? All devices exhibit opposition to the flow of current. Conductors have almost no opposition, while opposition of a load is considerably higher. Insulators have extremely high opposition. So in formulas, resistance is represented by either R for resistance and then X of C. This is what's called capacitive reactance, and X of L is inductive reactance, which you don't really. So these are true Ohm's law right here. So in Ohm's law, this should not be V is equal to I times R. This should be equal to V is equal to time times what? Ohms. Whether it's reactance or resistance. So ohms would equal to V over I, and then I would equal to V over ohms. So R could be replaced by X of L, X of C, or Z. In any of these formulas. We okay? Of course, y'all probably worked 100 of these problems. We usually throw these in there because this class only has EET 100 to get through into the course. So we usually have them. Everybody okay with these? Calculating R, I. Everybody okay with Ohm's law? In an ideal circuit, all the push provided by the voltage source will be distributed across the loads. Current flowing through opposition of the load produces work that the circuit was designed to deliver. Not only does it produce the work, but it also drops the voltage, right? It drops the pressure. In a real circuit, all devices have some resistance and or reactance. Even conductors have resistance and reactance. So it means conductors are going to drop a voltage. We call it, Alabama Power has to deal with this more than we do. They call it line loss. And they have to deal with line loss all the time because all conductors have resistance. The amount of resistance the conductor exhibits to the flow of current is determined by what? Temperature. Temperature, yeah, but I put insulation in there because in the NEC code for ampacity, that's what they give you. They give you the type of insulator. Because the thicker the insulator is, right, you understand that, the more heat it's going to keep you. And metals vary their resistance with temperature. The hotter they are, the more resistance they have. Material size and length of the conductor. Also, if the conductor are improperly, so sometimes we put resistance into the conductor just by the way we route them or the way we terminate them, right? You understand that? And of course, the amount of reactance is determined by frequency. Okay, the amount of push available. Anytime we go through an opposition, we're going to lose some of our push for the other circuits down the line. Right? You understand that? And then that in DC. And of course, V is equal to I times R. Are we okay so far? So this is an ideal circuit. Now normally when we calculate a circuit, we calculate it as ideal. Because everything we have has a tolerance to it, right? Understand that. So back in DC, what did you have to do with your resistors? You measured. And then when you did your math, you didn't use the color-coded value, you did the measured value because you were trying to prove V is equal to I times R. So you measured the current, you measured the resistor, and you found out that if you use the measured value, you always come up to be almost exactly right. When you get into the field, when you get on out there, we don't worry about tolerances anymore. We calculate everything with their color-coded value or their indicated value. Because then we understand we've got tolerances. So that means if I calculate 5.83 and I come over here and I get 5.21, I say, well, that's okay. Because what's the difference between my calculated, which is perfect, and my measured? Well, when we calculate, we assume that everything's perfect. And in electronics, guys, you're going to run into tolerances all the time. And if we had to measure every device, we would have problems, right? You understand? So even engineers, you know, they anticipate that their circuit is not going to respond exactly the way they designed it, because they might calculate a 333.2354 ohm resistor. Guess what? You can't buy that off the shelf. You could put a rheostat in there and set the dang thing exactly where you wanted it, but over here I paid 10 cents for that resistor. Over here I paid $5 for that rheostat. Yeah, 10 cents, right? In fact, less than that. If we buy in groups of hundreds, we're going to throw almost nothing. So this is what we end up in an actual circuit, is we end up with the actual conductors having a what? Having a resistance. I'm using 0.1 ohms. What determines the resistance of the conductor? Temperature. Well, that's temperature. Temperature, size, length, and material. All right, understand. So how do we compensate for the resistance? How does Alabama Power compensate for the resistance of the resistor? So that means, let's say I'm trying to run. Now, what do we pay for? Do we pay for voltage or do we pay for current? We pay for power. So let's say I'm trying to run a 1,000-watt load over here at 10 volts. Let's make it even. So how much current would be required to run a 1,000-watt load at 10 volts? Now, you got to understand, loads are designed around a voltage. So you can't say I'm going to take something that's designed around 120 volts and put it on 240. It'll pop just like that, right? Understand that? So loads are designed around a voltage. Every sure enough load you see is designed around watts, not current and not voltage. So what would be my current, guys? Okay, so if P is equal to I times V, then I is going to be equal to P over V. So if we got all of it out there, of course we're not, that's going to be what? There's a 1,000, we wouldn't say 1,000 milliamps. So 1,000 divided by 10 would be 100 amps. So I would be sending out 100 amps in there. Right? So that 1 point, this wire now would come up here and drop what? So it's going to drop. So we're not going to get 1,000 volts out there. We're not going to get 1,000 watts out there. So V is equal to I times R. So V would be equal to 1,000 times 0.1 ohm. So how many volts would it drop? Wouldn't work, would it? I got problems. Huh? Well, I don't even have 10. So all the thing would never work, right? You understand? We would actually end up distributing it out. Let's say I raise my voltage up to 100 volts. What do we got now? So instead of 100 amps, we got 10 amps. Well, now this guy right here is going to drop less voltage, right? You understand that? So I'm going to get more voltage to the load. Let's say I go to 1,000. Let's say I go to 1,000 volts. Well, let's say I go to 10,000 volts. 100 milliamps. Let's say I go to, right? You understand what we're going. So if I'm dealing with power, the higher I can make the voltage, the less current is going to be. These conductors are going to drop less voltage because V is equal to I times R. So what does Alabama Power do? So what voltage is available up on those power lines coming into your transformer to your house? No, that'd be dangerous. You're getting about 23,000, about 2,300 volts. Now, if you got into 2,300 volts, it's going to kill you dead, right? You understand that? But now they can deliver 2,100 volts of power to that transformer, right? You understand, with 1 amp of current. Now, when they're trying to transmit power from here, so here at Bessemer State Technical College, not Bessemer, Here at Lawson State Industrial Campus, our power comes from the Tennessee Valley. How long do you think those conductors are? A lot of miles. About 200-300 miles, right? I understand. So what do? Do they run wires bigger than me? No, you look at those wires, they might be that big. Because they raise the voltage up so high. So probably coming down from that distance, they're probably over almost 800,000 volts coming down through them. So 800,000 volts, they could deliver what? 800,000 watts of power with 1 amp. So what advantage we have to the high voltage is we can deliver the same power at less current. And the smaller the current, it means what? The smaller the gauge wires we can use. So instead of using copper, I might go to what? Aluminum. Right, you understand? Even though it's way down the chain, aluminum is almost a semiconductor. It's got 3 electrons out there. Aluminum. But it's a lot cheaper, right? You understand that? So basically what they try to do is they try to get, if I'm running real high wattage loads, I want to run it at a higher voltage. Because that means I can run smaller conductors, right? You understand that? If I'm running real low wattage loads, I'm going to run those at low voltages. Why? Because they're safer. So the advantage of low voltage is it's what? Safer. The advantage of high voltage means I can deliver power at a lower current, which means I can use smaller gauge wire, or I don't have as much line loss, right? You understand that? Cheaper to install, not cheaper to run. Watts is watts. We pay for 1,000 watts. I can deliver 1,000 watts, right? I can deliver 1,000 watts at 1,000 volts, and I still pay for what? 1,000 watts. So out of my power, if technically, guys, and this is what we talked about last class, technically, if my transformers were 100% efficient at stepping this voltage up and stepping it down, if you turned on a 100-watt light bulb at your house, then your power plant would give you 100 watts. And you'd pay for it, 100 watts. But nothing's 100% efficient. Transformers are well over 95% efficient. So here's an ampacity. This is a resistance chart right here. We call it the American wire gauge. European wire gauge is used as more. In fact, this could be a combination of both because this gives what? Millimeters. So in house wiring, what's the 2 main wire gauges? Well, we actually use 3. Depends on whether you got some real high current stuff. We use a lot of 14 gauge. And this is the size of the conductor. This is the ohms per 1,000 feet. So 14 gauge wire is 2.525 ohms per 1,000 feet. But that is at a temperature. They didn't give us a temperature here. I don't know where I got this chart. Usually it's about 20 degrees centigrade, which would be 68 degrees Fahrenheit, right? Because ohms do what? These ohms are going to vary with what? Temperature, right? Understand? This is what we call an ampacity chart in free air. What does that mean, free air mean? It means it's uninsulated. That's what free air means. It's not insulated, so it's exposed to the air. The conductor itself is exposed to the air. So 14 gauge wire in free air could handle how much current? 32 amps. Are we okay? Any problems there? Now, when National Electrical Code puts out the ampacity chart, what are they going to try to consider? First of all, this is free air. These are, if we run the conductors in less than, these would be single conductors. This would be multiple conductors. As soon as I put conductors side to side, and we got both of them conducting current, then that means they can't handle as much current, right? You understand, because of the heat generated between the two is going to add up. Okay. So if I run more than a certain amount of conductors, or then I'd have to reduce the ampacity. What other things would have? So what's ampacity? What's the term ampacity mean? What do you think that means? It's a combination of two words. Yeah, it's amp capacity. So it's the amperage that a conductor can handle. So a conductor doesn't deal with volts. A conductor deals with amps, right? That's what it's trying to get from power source to your house. So if I were to start taking this thing, first of all, when I put insulators on it, what should happen to the ampacity? Should it go up or go down? It should go down, right? If I run this through the ceiling of my house, is the ampacity will go up or go down? Well, you have to rate it for when it's not when it's winter, when it's what? Summer. So the ampacity would have to go down. If I run it through my walls, the ampacity would have to go down. If I run more than a certain number of conductors, the ampacity would have to go down. So what National Electrical Code has done is when they dirate these things, dirate means degrees by, is they basically bring it in the worst case scenario. So if I run 14 gauge wire inside a house, if I use the ampacity listed by NEC, it should meet every situation I could possibly think of, right? So here's the ampacity chart coming off the National Electrical Code. So they rate a 14 gauge wire at what? 15 amps if it runs these insulators, 30 amps if it runs those insulators, and then it's not rated at this right here. So all these up there, these are different types of insulators that an electrician would understand. A standard house wiring uses what they call Romax, which is Teflon. So this would be what they would rate it for if you're using a 3-wire conductor, right? Or 2 conductors with a ground. Right? Y'all know what Romax is? Ever seen house wire? It comes in a white jacket. That's Romax. The first company that came up with that was a company called Romax, and they have the privilege of it being their name, even though I don't know if Romax is in business anymore. So electricians call that standard house wire, and they call that Romax code. And it comes 3. You can get a 2-wire with the ground, right? Understand? So it have a black, which is electricians call it your hot one. Then we have the white. They call that what? Neutral, and then the ground. NEC, you'll never see those terms in the national. So if you're going to run it inside your house, this would be the chart that you need to use. Some of these are good for outside, some of them are not. So. Are we okay? You can look up NEC 310.15, and it'll tell you, when you look that up, it'll probably bring a picture of the code book up and show you how much further you need to decrease this by if you ran it across the ceiling. So if you ran it outside, right, across a roof, you would have to dirate it some, and if you put more than 2 cables in a trough. So here's our power formula. Is everybody okay here? So this is the main one, this is the secondary, this is the secondary. Why is it important to know how to calculate power? Huh? Power is work, guys. So of course companies do that. It depends on how much work they do. I wish they paid the city employers by that. You see them trucks all over the place, and people be y'all done plenty of power formulas, right? This is a problem that people aren't. So if I double the voltage to the circuit, what happens to the power? Now this is not the load. This is not the source. This is power. So if I double the voltage to a circuit, what happens to the power? It increases, but by how much? Here's my blank sheet. Well, we'll calculate it out. We'll do a real easy one.
All
And we'll do a DC one. And we'll start off with 10 volts. At 10 ohms. So we can use power, we can use our I square R formula. So that's going to be 10 squared, right, times 10 ohms. What would be our power? What was that? 1,000 watts. Okay, so let's double our voltage. So we're going to double it. So we'll go to 20 volts. So my power is going to be equal to 20 squared times 10. So if it doubled, it would go to 2,000 watts, right? Huh? That's 4,000 watts. What people don't understand is, as far as the circuit concerned, so power is equal to V times I. V and I are directly, if the resistance does not change, V and I are directly proportional to each other. So what that means is if you double the voltage, you double the current. Right? You understand that. If you triple the voltage, you triple the current. So power varies with the square of the voltage. So what will happen if we half the voltage from our original situation? So now we're going down. So instead of using 10 volts, I'm going to use 5 volts. But power is going to be equal to 5 volts squared times 10 ohms. 250. Well, what did it do? It dropped down by a quarter. So if you go down, it varies with 1 over the square of the voltage. If you go up, it varies with the square of the voltage. So this is why you take a light bulb that's rated at, 120 volts and you put it in 240 volts, it blows before you can get it turned on to it because it's trying to deliver 4 times the power. My mother called me out there to her house one time and said, she said, Rich, my stove, electric stove, won't even boil water anymore. And I went out there and measured her 240, and it was only 120 volts. So her outlets was only putting out a quarter of the power, right? You understand? What had happened is she had lost one of her drops coming down from the transformer. We had to call the power company. But as soon as I measured the output of the coming out of that outlet, and it said 120 volts, I knew she had big problems, right? That makes sense. So here's our power formulas. There's a ton of them.
Will you hold that? I know.
Well, we're not going we're not going to use these formulas, guys. These are nice to know, but we're not going to use them. All I want you to do is have a. So if the voltage is not right, if the voltage is less, if it's less, then remember it's going to be 1 over how much less it is, right? You understand? If it's more, it's going to be. Right? It's going to be the square of that. So that's why Alabama Power, and this is why we have brownouts, but also why somebody's house might have exactly the same hookup that you got, and their power bill might be more than yours. Or you might have another neighbor's got exactly, and that wouldn't be a neighbor, but somebody down the street got exactly the same house you got exactly the same appliance you have, and their power bill is less. Well, what's the problem? Well, when Alabama Power says, NEC knows this, so NEC talks about the 2 voltages we have in our house is 120 and 240. What's the average of your house being 120 and 240? Slim to none, because you don't have a regulator, they feed you through transformers. Now, they have taps on their transformers when they hook it up, and they try to get it as close to 240 as they possibly can. But they'll never actually hit it, right? You understand? So if this house over here, their voltage is a little less, then odds are they're going to pay a little less power bill. But you can't put it too much, or your motors or stuff won't run, right? You understand that? So everything's rated over a voltage range. Shorts. Now this is probably one of the most misused. Oh, you don't want to write. You want to write those down?
No, I got other ones I need to write down.
Yeah, they're up on slides, right? Y'all can just get on. So we have two types of shorts. We have a short and we have a short circuit. Now the problem is when you get out on the field, guys, where people don't know, if they've got a problem, they say they got a short. It's got a short in it. Right. My mom used to call it a shortage. It's got a shortage in it. Say, okay, Mom. But she's usually talking about an over. So a short is an undesired, current is flowing, it's just that we've lost control of the current. It's an undesirable path for current flow. Shorts will always cause the total resistance in the circuit to go down. If the total resistance goes down, then the total current will go up, right? You understand that? Always. So we can have a short without a short circuit. So what's a short circuit? Short circuit is when your source conductor and your return conductor come in contact with each other. That way you've lost the resistance of the load. So now the only thing limiting the resistance of your current is the resistance of the power source. So every power source has a resistance and the resistance of the wire. So current will go to the maximum it will go to. This is what overcurrent protection devices protect against. Overcurrent protection devices don't protect against short, they protect against short circuits. So NEC rated a 14 gauge wire at 15 amps. So a 14 gauge wire would run on a 15 amp breaker. Right? Sources of short, incorrect splicing, incorrect termination, defective load, and also current. If we lose our insulator, this happens every once in a while in a car. Because cars have got so much vibration to them. They don't tire those wiring harnesses down good enough, and they get up against something. Over time, what's it going to do? It's going to wear off the insulation. I'm laughing because we put some wheel well lights in my grandson's Jeep. And when we tied it down, we had a spot that wasn't tied down real good, and it was up against the Jeeps. He's got these big old tires on it, and they're jacked up, so it's, and over time that sucker shorted out and melted the wires. But it was because of what? Because of that chafing, wasn't it? Chafing. And this happens every once in a while. And they tie houses down really, really well. When they staple them down and everything just to prevent the vibration of your house. Transformers, we got a big problem because them suckers are vibrating all the time. You can hear them suckers hum, right? They got all kind of wires inside there. And that magnetic wire that they use almost has no insulation at all. So they'll epoxy those things. They'll get them as tight as they could, and they'll dip it down in epoxy just to keep those wires from doing what? Trying to keep those wires from vibrating against each other and wearing them. Are we okay? All circuits must have resistance. If not, according to previous formula, the current and the power. So I is equal to V times R. We have 0 R, so V, any number divided by 0 is infinity. I could put that on the test, and somebody in this class would say 0. So what is division? Division is a repetitive subtraction. We learn multiplication tables so we don't have to do it. But the problem is that in what we do, when microprocessors first came out, they couldn't divide. They did not have an instruction that divided. They could do two maths. They could add and basically subtract. So I mean, to do math in these early computers, we had to write a program to do math. And what you do for division is you use what we call repetitive subtraction, which is what division is. So we take our we take what we want to divide in, and we start subtracting what we want to divide by, until we generated a borrow, which means we exceeded the number. How many times can you subtract 0 from a number without borrowing? Infinite. So that's why when you say any number divided by 0 is going to come up, and your calculator is going to give you an error. Why? Because it can't display infinity. And it depends, so technically the power's going to go to this. Now what, it's never going to do this. Hopefully you got an overcurrent protection device. If you got a short circuit, guys, somebody is going to give up. So these little old batteries I have in my pocket, you know, if I carry a battery in my pocket, the battery's going to give up, right? You understand that? Because of its internal resistance. You got a regulated power supply, means if the voltage tries to drop down, it puts more energy into the power supply. So what happens is that we get into these regulated power supplies with that dang car battery out there. That car battery's got hundreds of amps available. You get a short circuit on a car battery, guys, you got problems. Because what happens is those batteries will blow up on you. Because they're not, especially the sealed batteries that most people have now. Most of your batteries, you can't put water in anymore. They don't use water, they use a gel in there now. And those things are sealed up really good. You heat things up, what do they want to do? They want to expand. You put a lot of current through that car battery, it heats up, got nowhere to go real fast, and that car batteries will blow up on you with short circuits. Of course, the current flow will never go to infinity. If the load is bypassed, the current flow through the circuit will be limited only by the resistance of the conductor and the internal resistance of the voltage source. If not, they're protected by some overcurrent protection device. And we have two overcurrent protection devices. What are they? One starts with an F and one starts with a C. Fuse and a circuit breaker. Of course, what advantages of a fuse of a circuit breaker? Cheap, but what's the advantage of a circuit breaker? You can reset it, right?
I got a really random question. Like, in our house, one of our circuit breakers keeps, like, it's like something killing it over and over again. Is that because it's short or something somewhere? Like the breakers, we keep having to replace it.
Yeah, usually that indicates that you're running it close to its capacity. Technically, circuit breakers, you're never supposed to run over 80% of their capacity. So a 15 amp breaker, you should never run it over 12.5 amps. And the closer you get to the capacity of it, the more problems you're going to have on it.
So would it be bad to put a stronger breaker in? Or?
Yes. And why is that? Because it's rated at the current carrying capacity of your conductors. So you go in there and you put a 50 amp breaker in there on a 15 amp circuit. We'll be reading about your house on the news, especially if you're having that problem. We have people that do that. So now what's happened is you exceeded the current rating of your. What you need to do is add another circuit, move stuff off and over to another breaker. And those breakers aren't cheap, are they? Breakers are not cheap. So what happens if you're overloaded a circuit? And it's hard to do because they do all the, we parallel our house, but we don't do the parallel at the source. We do the parallel out in your wall somewhere, right? You understand? So it's hard to move things onto other circuits.
I guess it's like you remodeled the room where it keeps doing it and added more stuff,
And left it on the same circuit. Yeah. What you should have done is you should have ran another circuit into it. And then put some devices on one, leave the ones that's in there alone, and the new stuff that you added, put it on another circuit. Most houses don't use all the slots in your panel that's available. And if you got anything that's getting hot out there in the wall, you need to be careful. Yeah, so overcurrent protection devices are in there to protect those conductors getting to your load. Because those are the things that's running through your walls, right? Of course, the problem we have with a regulated power supply, what a regulated power supply does is it automatically adjusts its output to try to maintain a constant voltage. So we're going to create a short circuit in here probably next class with the big boy over there. It's a 40 amp. That's a 40 amp DC supply over there. So I need to make sure it's working. And we're going to do a short circuit and show y'all the disasters of a short circuit. But what you'll see is it's a regulated power supply. But as soon as I short it out, I might have 30 volts out here, but as soon as I short it out, it'll drop down to 2 volts because it it can't put out that energy anymore. And I'm going to come over here and I'm going to put a wire there, and the wire's going to start getting hot. Well, as soon as the wire starts getting hot, its resistance goes up, but this power supply is trying to regulate it, what? 30 volts, so it'll go up. And it just cascades after that. So eventually what's going to happen is all the insulation will burn off the thing. We might move it over to the classroom next door and give it time for the smoke to clear. But what'll happen is all the insulation will disintegrate off the thing. And then once your insulation is gone, and if you've got multiple conductors inside that raceway, then you got big problems, right? So when current flows through resistance, what happens is the metal heats up, the resistance goes up, which lets the voltage on the power supply go up because it's conducting less, which basically just cascades. The more heat is the conductor, something does not limit or stop the current flow, the conductors get extremely hot and may eventually do what? Melt and cause fire. So anytime you see when they're talking about it was an electrical fire, that's what they're talking about.
What causes a short circuit again?
Short circuit is when your source conductor and your return conductor somehow come in contact with each other.
How that happens?
Well, it happens when the insulation wears off. It happens when people don't splice or terminate correctly. It happens when people don't tape up correctly. It happens all the time. So it's running a device through a real long extension cord. This happened to me. I had a Vega GT, first new car I ever bought, and we pulled a trailer from California, so I wired into my lights and left the cord hanging up there. We had a dog. We had Alaska Malamute, beautiful dog, and the Vega GT was a hatchback, and we had a dog chain back there, and the dog chain had resistance in it, right? You understand that? And it came across the carpet and went down and got onto the common of my car and got into my taillights over there, or to lights. And I was driving along and my lights dimmed down, and I drive along and it dimmed down and I saw flashing in the back and it caught on fire. Well, this is the problem you have with these extension cords. You run them all over the place. You don't use the right gauge wire. You just use these little thin wires, right, to understand, because they're cheap. You go out here to Dollar Tree and buy one for $2. They use very small gauge wire. Then you run it somewhere and you hook your vacuum cleaner up there, 100 watt, 200 watt vacuum cleaner. And what happens? The wires get hot. Well, the wires get hot. It's got that cheap plastic insulation on it. What happens when they get hot? It melts off. So as it melts off, what happens? Then your source and comes in contact with each other. The dang thing has enough resistance to prevent from blowing your breaker, but now it gets red hot. And what does it do now? Catches on fire. So, guys, your outlet should never get hot. So if you got an outlet that's getting hot, it means you need to replace that thing or get somebody to come in there and replace it. Because the hotter your copper gets, the more it oxidizes. The more it oxidizes, the more current it gets. Now you get down here down the line, you plug something in, and it's trying to pull it through that R. Now you got I square R, and the dang thing gets hotter, and everything gets worse, right? You understand? And it eventually starts burning your insulation off of it. I don't know if anybody's ever been in the electrical trade. You get in these boxes, and the insulation will be charred, and it'll be just like you can just peel it off because it's already that hard on it. So this is why it's important to use the right overcurrent protection device. But still, that's not going to replace you. That's still not going to replace you 100%. It'll help you on the wires that run through your wall, but it don't help you on those dang extension cords that we use all the time, right? You understand? So that means if you've got a 15 amp plug, then by George, you need to use a 14 gauge extension cord in there, right? You understand that? So usually it means is the insulations came into contact with each other. Alabama Power has a lot of problem with trees, especially in the rain, because rain water has a lot of impurities on it, and a lot of times it'll fall over the what? The tree will fall over the power lines. You got a short circuit, almost a short circuit. Blows them up. Power lines fall, touch together. I think I told y'all about the big tractor trailer, didn't I? I tell y'all guys about that? That was interesting. And they got out here and fixed that thing, they had it fixed by the weekend, so it was up and running. So here's our overcurrent protection devices. We have fuses, which are not that popular in houses, but you can still buy disconnects and stuff that's got these basic fuses in there. Guys, you're going to see a ton of fuses in these because there's so much what? They're cheap. And then, of course, these commercial circuit breakers. This is probably what y'all run to in your house a lot, right? Okay? So this would be an example of a short. Notice I've got a straight path through this right here. Now what's happened, this is a series parallel circuit. This load is going to have to make up the difference. So now this guy up here is dropping 0 volts. This guy right here is going to have to drop all the volts, right? B square over R, right? So a lot of times when you have a short circuit, it'll cause other loads in your circuit to fail. They use it open or stuff like that. So this would be a short. That's a short. This would be an example of a short, right? You understand? Somehow these two wires came in contact with each other. This would be a short. That's a short circuit. And this is the problem we have with a parallel circuit. In a parallel circuit, every short is a short circuit. In a series circuit, it all depends on where the short occurs. So what is a short? It's an undesirable path for current flow. We've lost control of the current. It will always cause the total resistance in the circuit to go down. Rid short circuits and allow the handling of conductors. We coat these conductors with what we call insulators. These are guys that have extremely high opposition of current flow. There's no such thing as infinite current, so there's always current flow even through your insulators. It's just so low you just don't know it, right? They call it volumetric current. Call the insulators made of a substance that says extremely high. Don't say infinite, because there's no such thing as infinite resistance, right? You understand that? So if you take a little 9-volt battery and you put it across an insulator, there's going to be current flow through it. It's just that it's so low we cannot measure it. Okay? Opens. So what's an open? This is the one people don't use most out in like everything that goes wrong, they call it a short, right? So an open allows no current to flow through the load. If no current flows through the load, no work is performed in that section of the circuit which open exists. An open circuit prevents current flowing through the entire circuit. So your circuit breaker creates an open circuit, right? But a light switch creates an open. If it created an open circuit, it means I went out there and turned off the switch and everything in my house would go out, right? Okay, sources, of course, we have open switches, we have fuses, circuit breakers, we have faulty splices, we have tension breaks where we ran conductors and we didn't allot for expansion and contraction. Just about everything we've got gets bigger, right? You understand? Rule of thumb in networking is to leave at least one loop. So if you ever look at a network panel, you wonder why everything's got these loops out there. And that's to allow for repair, and it's also to help compensate for what? For attraction and expansion of the building. In fact, this building right here, you can see the expansion beams, expansion slots all over the place. Like if you walk down this wall, you'll go over a plate. If you pull that plate up, there's a gap about that big, and what it does is it allows the whole building to expand and contract. So I've seen that happen before. People run wires, they don't leave any slack in them, they run them real tight. in house wiring, you're supposed to have at least 6 inches of slack coming out of your wall out of your box, right? So this series parallel circuit, this would be an open. So what would happen is these loads over here would be fine. They keep working. These guys over here stop, right? Because they don't have a complete path of current for them. That would be an open. Now loads 3 and 4 wouldn't work, but loads 1 and 2 would work. Now this would be an open circuit. So to get an open circuit, you're going to have to open up usually we open up, on electricity, we open up what they call the hot leg. So now nothing works, right? You understand that? So you got into your house and some of your outlets stopped working. Some of them just happened to me. My wife turned on her air fryer the other day and it stopped working. And then we noticed the plugs in line with it stopped working, but everything below that. And what had happened, one of the wires on one of the terminals in one of the outlets had come loose. And everything down below that didn't. So DC-AC. So what does DC stand for? And alternating current stands for AC stands for alternating. So here we're going to be dealing with all the current we're going to be dealing with in this class is going to be alternating current. So far all y'all have had is DC, and we're going to be dealing with 208 and 117, around 117 volts. That's why we got to wear those gloves, right? Anytime we're working on an active circuit. That's the only time we're not going to work on an active circuit. We can troubleshoot an active circuit. Anytime you're going to work on the circuit, and what we're going to do is we'll come in and we'll push in the big up button up there, and then we'll come up here and we can work on it that way. And we'll tag it out too, by the way. We tag out here. We do lockout, tag out, but I'm responsible for the lock in this class, and you'll be responsible for your tag. So we'll talk about that too. Flows in one direction. Everybody okay? Electrons are moving from one direction. So here we have a minus and we have a plus. Current flows from minus to plus, right? Or electron flows from minus to plus. Are we okay? Any questions there? Produced by DC generators, batteries, thermocouples, solar cells, piezoelectric devices electronically with an AC to DC converter, and then bioelectric. Like us. So we're bioelectric. We create electricity. And that's what they used on. What's the name of the metric? Metrics. They used this as batteries, didn't they? So these are examples of. So we have DC voltage cells. We have batteries. We lost the actual key terms for these little things right here. These are not actually batteries up in the upper left hand. Those are actually cells. And you might, if you're old enough, you might remember why they called them cells. But now everybody started calling them batteries because the batteries in cars. To get a battery, you got to have more than one, right? You understand that? So we create batteries most of the time with cells. So you notice when you put these things in, you usually hook them in series or you hook them in parallel. We hook them in series to increase the voltage. What advantage does a higher voltage have? Yeah, power with smaller conductors, right? You understand that? And then what happens if we hook them in parallel, hook batteries in parallel, we add current. Odds are not. Usually they'll have more than one. Some of them have 4. Some of them depends on. It all depends, right? Depends on who designed it and what they designed them around. Usually 2 is usually the minimum you'll see in the remote.
The only thing I ever really see a single thing is little circle flat batteries.
Like that.
Oh yeah, like that.
Oh yeah, I call them hockey pucks, but they're called flat packs, I think. DC generators create DC. Power supplies. You'll run into a lot of, you've already played around with trainers. Trainers have power supplies on them. You take it and you plug Alabama Power in, and you got DC power supplies on there. So that's what we call an AC to DC converter or a DC power supply. So on our trainers, I think we got 4 fixed power supplies, and then we have 2 variable power supplies. Solar cells, piezoelectric, and then thermocouples. These are just a few. These guys generate DC. Piezoelectric are what these lighters are. If you got a cigarette lighter or something. Of course, most people are vaping now. AC constantly swaps directions. The voltage source in an AC circuit constantly swaps polarities, which causes the current to be swap. So we don't have a minus and a plus in AC. Why? Because they're always swapped. So we have what we call the electricians call them hot, and they call them neutral. And that's the two lines. So that would, hot would be L1, and then neutral would be L2. Less expensive to generate, extremely efficient to transmit. So what we can do is we can step it up for transmission, right? You understand, and do what? Step it down for safety. Voltage levels can be easily changed by transformers. AC motors are less expensive per horsepower. So AC motors used to, if you wanted to control the motor, to precisely control the motor, the torque and the speed, you had to use DC. They came out, we'll find out later on how we can control it, because AC motors basically wanted to run at a set speed depending on the frequency attached to it. We came out with devices called variable frequency drives, and now AC is starting to dominate the variable speed motors and controls because there's so much cheaper horsepower. We can produce them by AC generators. We can produce them electronically, or we can produce it by bioelectric. So you probably play around with electronically because you cannot put DC on a speaker. How many of y'all got radios in your car? Now, how many people has an AC? How many people has? So you got a battery, you got an alternator, which is AC, but they convert it to DC before it gets anywhere, right? You understand that? So there's an AC, there's a DC to AC converter inside your radio, but it's done electronically, and that's one of the advantages of DC over AC is we can electronically control it. So I can take DC and regenerate AC if I want to, right? In fact, that's what this guy does right here, this function generator. So here's an alternator. Usually you don't see it. Sometimes the rectifier assembly is outside of the alternator. It depends on who makes it. Most of the time they put the rectifier assembly. A rectifier is a circuit that takes AC and converts it to DC. And it uses devices we call diodes. If you take solid state, if you're in the industrial electronics program, you'll learn how power supplies work. If you're in the AUT, you just take for granted they work. Because we're not going to get into the internals of the power supply. But what that does, it's an alternator. Now, why is it an alternator? Because alternators are a heck of a lot cheaper per watt than DC generators are. But we have to, in your car, we have to convert it over to DC because you're running a DC system in your car. So there's what they call a rectifier assembly inside. Mobile AC generators, power plants create AC, electric eels. What's neat about electric eels? We can put them in both categories. It uses 10 volts AC to stun, and then it uses 870 volts DC to kill. So that guy, it's bioelectric, which is pretty neat. Then, of course, some of y'all might have some of these for your car, DC to AC inverter. And then function generators, which you'll run into those several times in your. Are we okay? So my wife's fan's got an inverter built into it. It's got a 120 volt plug in there, so you just plug stuff into it. It's pretty neat. So the way AC power is generated, alternating current provided by a voltage source changes direction at a constant rate. The repetition produces a voltage waveform shown on the next slide, or we can show y'all this over here. So this is not outbound power. This is electronically, and of course we can come over here and let me get my camera over a little closer. So this is AC power. This is the way AC power is generated. So I'm using a function generator. So this is the waveform right here. And this is 0. Let me show y'all where the 0 reference is. So the 0 reference is right here in the center. This is 0 volts. So anything above the line is positive. Anything below the line is negative. Now what you need to see is it starts off at 0, climbs up to a maximum value we call peak. As soon as it hit peak, it starts doing what? Climbing down until it crosses 0. So the work we're going to get out of this thing is going to be an average work, right? You understand that? So these peak values are going to be a lot more than the work we're getting out. In fact, 120 volts AC would be 340 volts peak to peak to get 120 volts worth of work out. But that's no big deal because we set the voltage with a transformer, right? You understand that? Now what happens is these guys are current at a precise rate. And so what I'm doing is I'm not looking at the same signal. I'm looking at a signal, but it's exactly the same way every time. So what that means is, I can't do it with this oscilloscope. Let me take this off. Go here. No, that's not what I want. This is what I want. No, this scope's too good. This is a storage scope. I don't know if I can get one of the digital scopes though there or not. What time does class start? Guys, when I get up here lecturing, we try to take a 10-minute break every hour. So you got to take a 10-minute break. Every time I get around an hour, somebody needs to do what? What we're doing, y'all need to, if y'all don't see this thing over there, you know it's not what. Yeah. So let's bring back the animation. So it's generated in a circle, right? Y'all understand? And this is the way AC is generated. So generators work real well spinning. So that's why your generators spin. So they generate these sine waves, these AC generators or these alternators. So it generates this waveform that looks like this.
Maybe we should go back to slide.
Mm-hmm.
So you take the VP.
Yeah.
And take the sine of that, and it give you
The instantaneous voltage.
Yeah.
And that's why it's called a sine wave. Because we call this the instantaneous voltage, right? Where this is moving down this line right here. But this is going to be in degrees. So this right here, one revolution is going to be what? 360, right? You understand? And even if you use 270, it would come up and give you a negative. It would say, okay, it's going to be a negative something, right? You understand that? So this would be 90. The sine of 90 is 1. So if the sine of 90 is 1, that means at this point right here, the output's going to be maximum. And then the sine, and this would be 270 degrees. If you looked at the sine of 270, it's going to be a minus 1. So if I took a minus 1 and multiplied it by V peak, it's going to come up and give me a minus voltage, which is what it's going to be because it's in the negative quadrant, right? You understand that? Which is pretty neat. And that's why it's called a sine wave, because the actual voltage varies with the sine of an angle relative to 360 degrees. So that's one thing you'll find out in AC. We'll say, okay, each repetition, so we freeze it, right? You understand? We can freeze it. And then it's repetitive. So it's just like TV. Y'all know TV and movies is just a sequence of pictures. But they're flashing the pictures up, and if they don't change, everything appears to be stationary. When does it start changing from one picture to the next is when something changes, right? You understand that? And luckily, our eyes can only, your eyes have a certain persistence to it, so it takes a little while for it to absorb your light. And if they flash the pictures up there fast enough, we don't see the individual pictures. What does our eyes do? It just blends everything together. So your TV is pictures. Movies are pictures. Used to, you could see it. If you have old projectors, you could hear them stopping. It stopped at an instant of time when it was in front, and then it would advance it on. Now we don't see that. On computers, they call it the refresh rate. That's how fast they're sending the pictures up to the screen. Used to, we'd only do 60 frames a minute, and the problem we had, 30 frames a minute. The problem we had with 30 frames a minute, that some people would get headaches. They couldn't see the flashing, but they could. Their brain was picking it up. So they update the refresh rate up to something called interlace to 60 frames per second, and 60. What they did is they shoot the same picture up there twice. And then before they go to the next picture. And that eliminated a lot of. So if you ever go into the setting of your video, if you're getting headaches when you look at the screen a lot of times, you might need to go in and change the refresh rate. And I don't know where it is on Windows 10. I can show you where it is on here though. So this right here would be called a cycle. So that's one repetition, right? You understand that? Are we okay? Okay. It could also be in degrees. So this right here would be in 360 degrees, electrical degrees of one cycle would be 0 degrees of the next one. It's just like 12 midnight. What's 12 midnight? It's the ending of one day and what? The starting of it. As soon as that hits 12, you're seeing two things. You're seeing the ending of one day, but it's what? Starting of the next. This right here would be 180 degrees. This right here would be 90 electrical degrees, and this right here would be 270 electrical degrees, and in between them. So these cycles are occurring at a precise rate. So the rate of the cycles, we call that frequency. Oops. So what's frequency? The rate of the cycles. Alabama Power. Anybody know Alabama Power's frequency? 60 cycles per second. Now, of course, what has happened is that people that's fundamental in the development of a science get the privilege of getting their name used for everything. So we use Hertz. So Hertz stands for cycles per second. And we abbreviate that uppercase H and a lowercase z. That's the way you abbreviate Hertz. So we would say 60 Hertz would be the same as 60 cycles per second. Now, the voltage we get, the problem with doing an average is if I come over and average equal amounts of spaces on this side, with what's going on this side, I'd always come up and get 0. Because if I had a plus 1 over here and over here I had a minus 1, then what's the average of a plus 1 and a minus 1? 0. So what they had to do is they had to come up with a method of giving us we don't call it an average, we call it an effective voltage. They had to come up with a method so they could understand the amount of work, where your negative voltage does the exact same work as your positive voltage. Does that make sense? So they came up with something called RMS, and this is what your meter measures. Your meter measures RMS, which stands for root mean square. But that definitely is the root of the means of the square. A mean is an average, right? You understand that? Mean is another term for average. So what we would do, what they did is they come up here and they squared every measurement along this thing. And they did equally spaced measurements. Well, every time you square a negative number, it comes up and gives you positive. Then they take the average of that, and then they take the square root of the answer, and that's what they do to calculate RMS. Now for a sine wave, it always comes up to be V peak times 0.707. So you get 70.7%, and that's what your meter measures. So your meter measures RMS. Most meters use what they call, most of your cheaper meters just divide it by 0.707. But we do have what they call true RMS meters, which actually calculates the true RMS. Now what that means is that if we get non-sinusoidal waveforms, the 0.707 only works with a sine wave. If you get something that does like this, where your positive alternation is different than your negative alternation, then your RMS meter, if you've got a cheap meter, it won't measure that right. You'd have to have a true RMS meter. Now in motor controls and electrical, if you buy a true RMS meter, you're wasting your money. The 0.707 meters work just fine. If you're into variable frequency AC drives and stuff like that, then you need to get a true RMS meter. But that would be one of the situations where you do that. So in this class, that's why you can get a $90 meter instead of a $300 meter. Just because you say, I got a true RMS meter.
So we say true RMS?
They're very expensive. They actually have a microprocessor inside there that actually calculates the root of the means of the squares. And it should be true RMS on the faceplate somewhere. Yeah, so you got a true RMS meter. Have you ever really needed true RMS? Probably not. The only thing it deals with AC sine waves, AC waveforms that are non-sinusoidal. They're not a sine wave. The 0.707 only works with sine waves. That means I could take a sine wave, I could take that negative alternation, I could flip it around, and I could lay it on top of that positive alternation, and you could not tell the difference. They are exactly the same. If they're not exactly the same, then a true RMS meter would have problems. We okay? But you pay a lot more money for it. But there's probably a 90% of the chance that people that's got them don't want. Don't use it. So I imagine in the military, if they bought meters, it would be true RMS. All the oscilloscopes we had in the military were Tektronix. These are the guys, top of the line. Now three-phase, so cycle, one repetition of a sine wave, or 360 electrical degrees. Alternation, each half of a sine wave. We have a positive alternation and negative alternation. Frequency is the rate that the sine waves occur, measured in cycles per second or hertz. And then we have what we call the period, which won't come in to play in this class at all, but if you're taking AC, the period is the time it takes for one sine wave. It is the reciprocal of the frequency. It's just all. So frequency goes up, period goes down. Does that make sense? So if I know the frequency, I can calculate the period. The frequency is 1 over time. If I know the time, I can calculate the frequency. It's 1 over. I mean, calculate the time. If I know the frequency, it's 1 over frequency. Reciprocal. We use reciprocal so much because it's always the opposite of, right? The opposite of. That scientific calculators are going to have a reciprocal key on. We use them so much, especially in engineering and electronics. It's either going to be measured x. It's going to be x to the minus 1, or it's going to be 1 over x, whichever one. So a minus exponent means the reciprocal of it. Are we okay? Lost anybody? Three-phase power. Three-phase power. This is what Alabama Power transmits. And we'll look at why. Three-phase power generates 100. Your sine waves are 120 degrees, electrical 120 degrees apart. It's more efficient to transmit. It requires 3 conductors, but just to send single phase requires 2. So if I'm going to transmit 3-phase, all I got to do is add another conductor for the 3-phase power. Requires 4 conductors when a neutral is used. So we have 2 ways we can send it. Usually power is transmitted using a delta. A delta is a way we can transmit 3-phase power without a common. And then we have what we call a Y-wound, which means we can add a common or neutral. Primary used by 3-phase motors, 3-phase power supplies, and 3-phase motor drives. And of course for transmitting power, right? So all our motors are 3-phase motors that we're going to be looking at this semester. Now what the advantage of is trying, what are we trying to send? Power. Well, what we can do with 3-phase power is we can get, so these are the formulas for 3-phase power, V times I, so we can measure the voltage on any phase, if we measure the current on any phase, and then we multiply that times the square root of 3, or about 1.73. So that means we get 73, we can transmit 73% more power with adding 1 wire. And that's why 3-phase power is so good. 73% more power just by adding 1 wire. We don't double it, we get 73% by adding another wire. So this is why when you look at these high power lines, you'll see 3 wires running. That's 3-phase. If you see 3-phase wire running, then that's 3-phase. If you see 2 wire running, it's what? Single phase. If it comes into your neighborhood, it's probably single phase. But somewhere that sucker's going to hook up to a 3-phase power. We can see our power, 3-phase power running, and we got 3 covens, I guess you'd say. And one of them lost their power, and the rest of them didn't, but they was picking their single phase off of different phases, right? And you can actually see where it picks them off. So 3-phase power, this is what it kind of looks like. So we have power available all the time. So when this one's 0, this one's 100 degrees. So basically you have power available. It never goes to 0. And we'll show y'all something else where it actually creates a shift to cause a motor to rotate. This is the generator. So this is the way we generate. This is the way probably 99% of your power is generated. AC is generated by spinning a magnet through a magnet. Spinning a magnet, and this is usually an electromagnet, and then these are conductors on the outside. So what do we need to do to produce power using EMF magnetically? Anybody know? Some of y'all have taken my classes before should know that. So what do we need? Okay, so we need a magnetic field. And I'm paused. I keep threatening to say I'm going to put this on a test, but then because this is pretty important to know. Second thing we need. New conductor. What's the third thing we need? No, we're trying to produce the EMF. We're trying to get a voltage. Right? Relative motion. I'm going to pause this. I can turn it off and on, or I can control its strength. If I put more current into it, the magnet gets stronger. If I take less current into it, the magnet gets weaker. So what determines the mount? Number one, strength of the field. Yeah, the amount of EMF. Not the amount of current, the amount of EMF. One people won't say, the wire gauge. Wire gauge has nothing to do with the amount. What it determines is how much current you can get out of the dang thing. Because that's determining the internal resistance of the thing, right? You understand? You can use bigger gauge wire. You're not going to get any more voltage because it has nothing to do with the gauge of the wire. What it depends on is the number of loops. So notice mine, I've got what? I've got loops. So every time I induce a voltage, I induce it into those wires. All the wires are wired in the same direction. So what happens is the voltages add together, just like on a magnet. So the second thing would be the number of loops. And what's the third thing? The speed of the motion. The question on the test would be what's required to magnetically produce an EMF? What's required? A magnetic field, a conductor, and then relative motion. What do I mean by relative motion? I can keep the magnet stationary, and I can move the what? I can move the loops, or I could do what? I can keep the loop stationary and move the magnets. So what you did, if you ever looked at an alternator, you took it apart, what they do is they come over here, and on the back they have what we call slip rings back on the back. And then they'll have a little brushes running on like this. This will be on your car. So it allows this thing to spin, right? You understand? And it's got a lot of turns of wire out there, so we can produce a pretty strong magnetic field with a little current. I'm not getting my load off the rotor. I'm putting my electromagnet. So I come out there and I crank my, this is a problem we have with cars. This is constantly changing. It's the speed of the motion. So the faster you go, the more current your alternator or power your alternator wants to put out. The slower you go, the less it has to put out. But if you went out there and put your meter on there, it's going to measure about a little over 14 volts, no matter what you do, because it's got a regulator. So what the regulator does is if the voltage tries to drop down, it puts more current into the magnet, makes the magnet stronger, puts out more voltage, right? You understand? If it tries to go up, what does your regulator do? Put less current into your magnet, which causes the output voltage to stay the same. And that's what the regulator in your car does. So if you're sitting there mashing the gas and your lights are getting bright and doing that side, it means you're having problems with your regulator, right? You understand that? So you can go out there, you can roll your windows down, you can turn on your lights, you can have your air conditioner running. If you put a meter out there, it's going to measure right around 14 volts. It's not going to be perfect, but it's going to drop a little bit, but it's not going to drop much.
How would you know if you got a problem with your alternator if it has it?
Well, when it cranks up, if it cranks, your alternator should put out over 14 volts. It's a 12-volt battery, but it's a lead-acid battery, so to charge those things, we put more voltage and force current back through the battery. So a regulator should regulate it. So your battery, if you let it set overnight, should measure pretty close to 12 volts. You should pretty close. So if you go out there right now and it's measuring like 11 volts, and that means either the battery's bad or it's not charged. Jump your car off, crank it up, and if the alternator's running, if it's got any juice, if it's got any current available at all, in fact, it's going to generate itself. It should go up to over 14 volts. If it's coming up 14 volts, then that means your alternator's good. and your problem's in your what? In your battery.
But with the regulator, just say if I got a bad alternator, but it got a regulator, it's when I go out there and put my car on, it's still gonna measure 14 whether it's good or bad.
No, your battery only puts out 12 volts. Your alternator puts out 14. If you measure 14 volts, your alternator's working. You're not going to get 14 volts.
I got you.
You don't get 14 from the battery.
You don't get 14 from the battery. You get 12 from the battery. Now, if you turn it off and measure it, your battery's going to measure. We call it it's a surface charge, where it's going to measure over 12 volts if you just turn it off. If you set it overnight, it should measure 12 volts. Yeah, pretty close to 12 because it's 2 volts per cell. It's 6-cell battery. So we can regulate this stuff, and that's what's on Alabama Power. They regulate their output voltage, but the problem is they regulate it at the power station, right? From then on, they're depending on transformers. So that's why it's such a wide. 120 volts plus minus 10% is legal. So that would be anywhere from 90-something volts up to almost, would still be considered legal to your house. So all I got to do is just take coils out here and spin them. If I offset the coils by 120 electric degrees and put 3 wires on, I get 3-phase. 3-phase generators cost more, but we saved it up on being more efficient for transmitting power, right? We get 73% more power transmitted over just adding 1 more wire. But I get down to my low power loads, like my house, it would be more expensive to run the extra wire out there. Because now I got to have 3 transformers on the pole out there instead of what? Instead of 1. So industry is going to have 3-phase. We have 3-phase here. We have 3-phase. So you go over there and look at our substation. We got our own substation over here. It's got a 3-phase transformer. You see 3 wires coming in. You see 3 wires coming out of the transformer. I don't know what they sent around the perimeter here. So this is 3-phase. And of course, I've seen these guys all the place. 3 nice big wires. They usually run them in groups of 3s. And what that does, it allows 1 wire to break, and there's still, and also it reduces the gauge of the wire. So if you hook 3 wires in parallel, then each one, the current would split up between 3, and each conductor itself would only be carrying 1/3 of the current. So usually they run in groups of 3s. I've never seen them run more groups. So what that does is it allows them to use a smaller gauge wire, so now they can put it on a spool, right, and unspool it. And also it's aluminum too. What advantage does aluminum have over copper? Cheaper. And the powers are going to be cheaper because the aluminum weighs a lot less than copper. Copper's heavy. So AC seems great. But what the AC is real hard to electronically control. So we can control electronically control DC. In fact, what did I just tell you? We could take AC, convert it to DC, and then convert it back to what? AC. But now I'm controlling the amplitude and I'm controlling the frequency. Alabama Power controls that 60 cycles. And it's precise too because of step up, step down, step up for transmission, step down for what? So the lower the voltage, and also we can start dropping it. And you look at these high voltage lines, how high are those lines up there? Because them suckers are looking for ground. I don't forget it takes like 11,000 volts to arc an inch or something like that, and them suckers are doing a couple 100,000 volts. So they're all looking for ground, earth ground, right? Understand that? So they get them suckers way up. So when I start dropping them down, they get safer, but also it means we can get them down what? Lower to earth ground. Until we get to your house. And they're all uninsulated. Why do we want them to be uninsulated? Because they can carry more current, right? You understand that? Of course, we can't handle it anymore, but they can carry more current. And then the only place they're insulated is where? On your down drop to your house. That's where they're going to be insulated. Or to the plant. So these are, we can buy three-phase transformers. But usually Alabama Power does a lot of these on three-phase. And why is this? Now this is cheaper this costs more to install, but this is a lot cheaper to maintain. So on a three-phase transformer over there on the left, if it goes out, by George, you got to replace the whole transformer. On these, you only have to replace one. And if it's running what they call a delta arrangement, you actually can run it with two transformers, but each transformer is going to have to handle all the power. So you can. There's a lot of damage to three-phase as far as transmitting power. So just about all your high-powered companies or restaurants and stuff like that get three-phase, and then when we get into residential, we are considered to be extremely low power compared to the U.S. Steel's bill. When we worked out there, and everything was running, and Alabama and U.S. Steel had their own generators. They ran generators off the gas that came off the glass furnace. And Alabama, U.S. Steel, and our power bill was over $1 million a month, three-phase. Of course, they was making a lot more than that. And of course, y'all familiar with what we call substations, right? And we've looked at this. So if my transformer, and I have no line loss at all, then over here at our house we have 120/240. We use our low wattage devices run off 120. So that's what these outlets are. These are 120 volts, right? So I've got to access it. Your high wattage device run over 240. Where are your 240 plugs at? But where do they hide them at? They hide them. So they have to be mounted down on the floor behind the appliance. So to get to your 240 plug, you literally got to pull these things out, right, to get to them. And then of course some devices are hardwired, like water heaters and stuff like that. They're hardwired. If you want to turn those things off, you gotta go in and trip it off with your breaker, right? So we could see the advantage of this. I think that's the way this slide is, by the way, where we're trying to get 1,000 watts of power at 120 volts would be 8.3 watts. That would come up to our transformer. Our transformer steps it down for safety, right? Then up there we have 2,300 volts on our delivery system. That's what happens, right? So now over here on this line, we're getting 1,000 watts, but now it's only 435 milliamps. Right? To understand why? Because it's delivering that 1,000 watts at 2,300 volts. Then we go to a substation again. Over here, 275,000 volts, we're looking at 3.6 milliamps to send 1,000 watts of power. And then we go over here, 2,300 volts again, so we're back over there. So you can see what's going on there, and why the advantage AC has, because AC we can do what with it? We can step it up for transmission, right? You understand? Because I'm not trying to sell you voltage, I'm not trying to sell you current, I'm selling you power. And the higher I deliver that, the higher the voltage I use to deliver that power, the less current is required. Which means I'm going to be what? It's going to take smaller conductors. Basically, it. It's going to save me money on conductors and also make them easy to install. Are we okay there? That makes sense? And we've already talked about RMS, Rubin square. That's just a method of coming up with an average of a waveform that has, where the negative does just as much work as the water, as the positive. Are you okay there? Everybody okay with resistance? So what we need to do is we need to talk a little bit about reactance and impedance, and we're just going to talk about this. I'll let y'all go ahead and take another 10-minute break. in this class you don't really need to know, but you see I get a phase shift out of that inductor, right? You understand, which is very, very important. And then also I get a voltage drop, and the voltage drop is a voltage drop without any current, which is pretty neat. Resistors don't do that, but inductors do. So what happens, it appears like that inductor is doing electrical work. If I got an amp meter and I put it on the input of my inductor, I would measure an amps. I measure the voltage drop across it. I measure volts, and I'm going to say P is equal to V times I, and I say that inductor does work, but it don't do any work at all. So capacitors create an opposition called capacitive reactance. Inductance create an opposition we call inductive reactance. And in formulas, we represent them as either X of C or X of A. Somebody else taking AC, y'all going to run into X of C and X of A. Now, what we do is in an AC circuit that's got both resistive and reactive devices in there, we call the opposition in an AC circuit, we call it impedance. So what you're going to find out, what you're going to find out, people that deals with communication cables, they'll talk about impedance all the time, even though it don't have any DC resistance at all. So if you hear impedance, you know they're talking about AC. That makes sense? Everybody okay? Any problem? But they don't do any work, but they appear to do work. So what happens in an AC circuit, that's the formula, by the way. So what we do is we go out and we buy a capacitor, and you buy it by something called capacitance. It's in farads. So we go out and buy microfarads, or picofarads, or nanofarads, or stuff like that. Then we plug that into the equation. 2 pi, we use 6.38 units there. We multiply it by the frequency that it's running at. Then we multiply that by C, but notice it's 1 over. When I say 1 over, it means it's inverse. So with capacitance, what happens on capacitors, as frequency goes up, their opposition goes down. So capacitors won't pass DC. They'll block DC because DC has a frequency component of what? 0. So true DC. If DC is varying, it will let the variation pass through, but it won't let the DC itself. But it creates a phase shift, and it does work without it drops a voltage without producing power. So if you see a capacitor, you fill a capacitor and it's hot, it means it's bad. A capacitor should not be any hotter than the ambient temperature that it's around. Capacitors don't get hot. They could be, it looks like they might be conducting 1,000 amps, but the current is not flowing through them, it's flowing in and out of them, right? You understand? The analogy we use is buckets. So I've got a pump over here that's pumping, and it's pumping water out of this bucket and pumping it into that one, and then it reverses direction. Well, there's no flow through the buckets, right? It's what? It's in and out, and that's what capacitors do. The current flow is in and out of the capacitor. The current flow is in and out of the inductor, but there's no current flow through it, right? Now, inductors is a piece of wire, so there'll be a little bit of current flow through it. Inductors will get warm, but they will never get extreme hot. Capacitors, they shouldn't get hot at all. Unless they're leaky. So don't worry about that formula. If you're in AC, you're going to get this formula. So this is the formula for inductors. 2 pi FL. We buy inductors by something they call Henrys, and that's what L is. So we might buy, and this is why it got the name choke, because if the frequency goes up, it drops more voltage, right? You understand that? So they say it chokes off frequency. So you'll have people call inductors chokes. But inductors vary with frequency. If you double the frequency, the opposition doubles. If you half the frequency, the opposition halves. Inductors and capacitors are just opposite from each other. So if we get them in the circuit at the same time, they will cancel each other out now. If they have the same phase shift in the opposite direction. But we get a phase shift, right? You understand that? So thank God for phase shifts, because if we didn't have phase shifts, there would be no such thing as a single phase motor. because before a motor can turn, all your electrical motors work off the repulsion and retraction of magnetic fields. And one of the fields has got to do what? One of the fields has got to move. Three-phase, we have no problem because the fields are causing it to move. Single-phase, though, if you didn't create a phase shift, that dang thing would just sit there and hum at you. So we use these either inductors or we use capacitors to create a phase shift. So the three-phase motor will do, the single-phase motor will do what? Turn. So you'll find a capacitor somewhere on every single-phase motor out there. You'll find a capacitor somewhere, except for these little variable reductors. The phase shift. And so this is a picture of an oscilloscope. So capacitors and inductors cause what? Phases. They create a power called apparent power. Apparent power is rated in volt amperes. So when you go out and buy an AC generator, they're going to be rated in VA. Either voltage and a current, or they're going to be rated in VA. So Alabama Power has to generate AC, and so think about a transformer. Transformer is just nothing but turns a wire. So transformers create phase shifts. Motors create phase shifts. All right, you understand that? If your voltage and your current are out of phase, then your power is going to be out of phase. So it's real weird. Your maximum power don't happen at maximum voltage anymore, which is real weird. But we can compensate for it. So the power grid is predominantly inductive. So it tries to create a phase shift, what we call a lagging power factor. Capacitors like to create what we call a leading power factor, so capacitors and inductors cancel each other out. So this is why every once in a while you'll be driving along and you'll see a pole up there, a power pole, and it'll have these three little square boxes on it. And those are capacitors. And what they're in there for, they're in there to help do away with the phase shift. Substations have electronically managed the phase shift. They usually have banks of capacitors that they automatically switch in. They got a rotary drum that they switch in depending on the power factor, trying to get rid of the power factor. What is the power factor? In the motors actually have a rating, and we'll get over. So we got a plate on the motor called a nameplate. All your motors now have to specify a capacitor that you put in the circuit to take out the phase shift of the motor, to increase the efficiency of the motor. These old motors didn't have that. So all your new motors on the faceplate, it's got a little thing on there where you can figure out what size capacitor to put parallel with it. So in AC, we have two types of power. We have what we call real power, and we have what we call apparent power. We pay for apparent power. Your power grid has to handle apparent power. Your transformers have to handle apparent power. So that means companies are trying to. And resistive power is power that's in phase with each other. Your current and your voltage are in phase with each other. So we have to calculate that. So there's different methods. But what you can do is the power factor is the true power over the apparent power. And the ultimate goal for the company is to get a power factor of 1. That means your voltage and your current are in phase of each other. So we have different methods. We can use synchronous motors. We can use capacitors. We can use different methods to get those in phase. Alabama Power wants you to run, I think Alabama Power sets your power factor at 95%. You want to run it greater than 95%. If you get it below 95%, they charge you a penalty. Because why? It seems like they would want you to be out of phase because they get more money, but you got to understand their power grid has to handle that phase shift. So they would rather not have a phase shift at all. So that means if you've got a big phase shift, they got to have bigger transformers, they got to have big conductors, and it would cost them a lot more to support an out of phase power than it does for them to support an in phase power. So that's why their substations automatically do what? They shift phases. Then every once in a while, you ever seen those? Y'all probably notice them now. Every once in a while, you'll see a power pole up there, and they'll have these little square boxes. They won't be round; they'll be square, or they'll be little old tiny round ones. They're not transformers; they're capacitors. So capacitors basically eliminate what inductors do, or inductors do. So our power grid is predominantly inductive, because all your transformers are inductors, all your motors are inductors. So we call it power factor correction. And this is going to be on your faceplate of your motors. By the way, the closer you run your motor to its rated load, the less it shifts the phase, because it's inducing a voltage back into the motor. We'll look at that later on. So if you're going to buy a 30 horsepower motor running 5 horsepower load, then you're going to be paying more than what you think you are. So when you engineer these things, you need to buy a motor that's as close to the horsepower that you need to run, because they come ahead of the phase shifts that they create are a lot less. And last thing we'll look at, of course, conductor terminology. So we got a conductor. Conductor usually consists of at least a wire, but when we see them, they're usually going to be a wire with an insulator on them, right? And what's the function of the insulator? So you can handle it, plus we can get the wires close together, right, or the conductors close together. So we have printed circuit boards. So these guys that's on the printed circuit board, we call these traces. And usually the traces are copper. The exposed part, we go, but they use a lot of tin right now. Tin has a very low oxidation rate. And why they use a lot of tin to plate is because, number one, it gets along real well with solder. And number two, tin is a lot cheaper. And usually by the time these things start oxidizing on these computers, they're already out of date anyway, right? So originally, if you looked inside a computer, you'd see all type of gold plating inside that thing, but now you don't see much of it. What's going on? Can I get my camera to go all the way down? So this is a board that comes out of a computer, and I'll pass this around. This is not a good board. Normally you wouldn't handle this with your hands, because these guys can be damaged with static electricity, but I don't know if it'll show up or not. But these, can y'all see those little humps right there? Those are all conductors. Now on a printed circuit board, they call them foils, or they call them traces. So if this was a real motherboard out of a computer, we wouldn't be handling it. But the microprocessor is under that heat sink. So you should be able to see the traces. Now that's actually what they call a multi-layer board. So it's got traces. It's got traces running through the center there. Of course, everybody's okay on conductors. Some people call them wires, right? They're okay. And then we have what we call a cable. Now, technically, a cable is a group of conductors contained within a common jacket. So a jacket is not an insulator. A jacket, so an insulator, the function of an insulator, of course, the main function of an insulator is to keep that push inside that conductor, right, and not let it get out, because it's pushing, trying to push electrons all over the place. A jacket on a cable is there to protect the conductor from the environment. So you have different cables, different conductors, or different jackets that are specified for. So I wouldn't go out and buy Romax and bury it underground, because that jacket is not rated for underground, right? Huh?
So that's like when you see them on the side of the road and they're running that school orange.
If it's orange, it's probably fiber. But what you see is the orange is the jacket. You're not seeing the conductor. The conductor is smaller than a human hair, by the way. But you'll see them. You'll see them if you've ever been inside of one of these big gray, not gray, but the boxes the telephone company uses. You can see these big old cables coming in. That big old black thing that's the biggest thing up there on your power poles, that's a cable. And it's got hundreds of wires running through that thing. And that would be for people that takes you between switch boxes or takes you to your house. Some people still have wired phones. Huh?
So if that ever get cut before, then it takes hours.
Yeah, we used to carry a hardwired phone for years and years and years. But what has happened is that there's so many people now using what we call voice over IP. They're using the internet with a phone. It looks like it's a regular phone.
Yeah.
That there's hardly anybody working that's maintaining the lines now. So that means if you call somebody, it's going to be next week before they can come out and fix your phone. So my phone went out, and that came out 1 week, and he says, this wire's been in here so long, guys. He says, we're going to have to rewire that thing. He says, we can fix it, but it's not going to last very long. And when are they going to do that? Well, it might be years before they can get in there and reroute that. So that's why we finally went over to the voice over IP. But it can also be a conductor that consists of multiple layers. So we do have some high power cables. That'll be about 6 layers just to keep that push in. And then, of course, the fiber cable's got to protect that fiber. That fiber is glass, guys. Most of the time it's glass. And so they'll build those cables, and they'll have multiple labels. They'll have Kevlar in there, and they'll have all types of jackets inside there. Then we have solid strand wire. This is going to be one wire. Then we have stranded wires. This is multiple conductors twisted together to make the wire more flexible. And sometimes they're not even twisted together. I need to take that out. All we do is we take a lot of little old tiny solid strand wires, and then we put those in a bundle. We'll bundle them together. Sometimes they come straight through. Sometimes they're twisted together. Now, the only advantage stranded has over solid is that it's flexible. I don't know anybody running any house wiring that's solid. Very hard to deal with. That Romax they have, the 14 gauge Romax, it's hard to bend. It's hard to do because it's solid wire. What advantage solid has over stranded is solid. We can terminate it. We can wrap it around a screw and tighten the screw down. So we can take a piece of solid, we can put it in a loop, put it on a screw, and wrap it down. We can take it to splice it. We can twist it together. Stranded, we're not supposed to do that. Stranded is supposed to be in something that maintains the strands. Because if you've got one strand that comes out from under that screw, you've changed the gauge of the wire. And people don't know that. They'll take that stranded wire, they wrap it around the screw, they tighten it down, and half the wires come out from under the screw. So what we have to do on stranded wires is we have to put terminals on them. So we have these crimp terminals or these solder terminals we put on there. Or we put it in something where the strands can't get out. They have a horseshoe type thing. We'll put the stranded wire in there, and then we'll bring a thing down on top of it. And we don't allow the wires to do what? To spread out. We call it bird caging. So the advantage of flexible is, if you deal with stranded, you see some of these cables though, and they'll be that big and they'll be stranded. And each strand will be that big. Those things they're still hard to bend, but you can still, if you got the right equipment, you can still do what? You can still roll it around the scope. So these are traces. So this would be a string circuit board, and then usually it's covered. It's usually copper, and it's covered with a lacquer because copper oxidizes, right? You understand that? And then the exposed parts, we call these eyes. These are usually going to be tin plate. And then these are conductors. So these would be individual conductors. And of course, these would be cables. So this is Romax. This is yellow means it's a 20 amp cable. It's 12 gauge, and then the white indicates that it's 14 gauge. So they're even colorful. You would say this is 2-wire with a ground, so this is your ground, this is your neutral, and this is your, what they call a hot lead. EC calls this lead right here the ungrounded current carrying conductor. They call this the grounded current carrying conductor, and then this is ground. So if you ever looked at your box, the neutral is connected to ground. So why don't we use the neutral as a ground? So what's the difference between the neutral? The neutral is reference to ground, and then ground is reference to ground. Why do we use a ground? If the neutral is reference to ground, why do we use ground? Why do we run a ground? Why is a ground required? Originally, they what? Originally, if you got in real old houses, they don't run a ground wire. It's 2 wires, period. They don't run a ground wire. So the ground wire, the neutral is supposed to carry current. That ground wire is not supposed to carry current. So if I get any flow in the ground wire, it means that current is going somewhere else, right? You understand? It means you got not only a short, you don't have a ground. If this wire came in touch with that ground, you'd have a short. If this comes in contact with the neutral, you have a short. This guy is not supposed to handle current. Okay, you understand? This wire is. So they call this the ground. So NEC does not call that neutral. They call it the grounded current carrying conductor. And the black wire, they call it the ungrounded current carrying conductor. So what happens, we have to understand is that we're trying to make this safe as possible. We know that current kills, right? So normally if you get between the black and the white, you are a load. You're a light bulb. If you get between the hot and the ground, then something's wrong. So normally when we get shocks because somehow we get against ground, right? Y'all understand that? So we have these special circuit breakers called a ground fault circuit breaker. And what they do is they compare the current flow in the black lead with the current flow in the white lead. As long as those match, then we have no problem. If they don't match, what does that mean? It means the current is going somewhere else. So what we can do is we can put a breaker out there that if it's got a misbalance of like 10 milliamps, it'll pop it between the hot and the neutral. And these are called ground fault circuit breakers.
Ground fault?
Yeah. GCI. Ground fault circuit interrupter. GFCI. And you should have a ground fault on anything that's close to a source of water. So if you got any outside plugs, it should be on a GFCI. If you got a plug in the bathroom, it should be on a GFCI. Next to the sink. If you got one in the kitchen, you should have a GFCI. Within, I think it's 8 feet. If you got a plug within 8 feet of a water source, it's supposed to have a GFCI. Huh? It's got to reset back on. It's got to push the test too.
Yeah, the red and then the black.
It's got to push the test. And what's nice about those GFCI, so y'all know the way houses are wired. What we do is we have a panel box. And then coming out of the panel box, we have one wire and then we have a circuit breaker. And then we come over here and then we have our plugs. Now you would think the plugs are wired in parallel, but really they're not. Normally what people do is it's got 2 screws on the side. And what I would do is I would bring my hot into one screw. This is the way most electricians work. Good electricians don't do it this way. But what I would do is I would bring, and you can tell the difference. So if I got a plug up here, yeah, I'll pass this around. This is an ungrounded. This wouldn't be legal anymore. This is ungrounded. But you've got two screws that are brass. This is for your black lead or your ungrounded current carrying conductor. And then you got two screws that are silver. You'll see this. So this is where your black wire goes. This is where you, but look at the way they got it. They got two sets of screws. So normally what most electricians do, it's the fast way to do it, is they'll bring this black wire and they'll bring it in there. And then they'll take this off here, off this screw, and send it on down to the next plug. And then you'll bring your neutral in. It'll go to this. Then they'll tap off this other screw and send it down to the next plug. And then the next plug will do all the same thing. This is parallel, guys. But if these screws become loose, you're going to lose whatever plugs are down line, right? You understand what I'm saying? So let's say my wire comes loose out of this one, and this is feeding all the other plugs. Well, what happens, it'll work up to this plug, but none of the plugs down below that will work, right? And that's what happened with my wife's air fryer. Now, good electricians will come up here and they'll bring their black wire in, and then they'll twist it together. They'll have what they'll call a pigtail and twist it together. I should be doing it like this. And then they'll send it out, and then they'll put a wire nut across this thing. I don't know what a wire nut is. And in that way, if a plug goes out, it's not going to kill any plugs down below that. This is the way good electricians wire them. But most of them don't do that because it takes time. This is real fast. In fact, we've come up now and they've got these compression, these plugs in the back where you just strip the wire and stick them in there. And you don't even have to screw the screws down. And those will wear out over time, guys. So I would never, ever recommend using those things. But you have a lot, they're available and they're legal. And they'll just strip the wire and stick it into that compression plug, and it's got little fingers in there that grabs it. The best way to do it would be this way right here, where you take your grounds, you take your hot lead and twist it, but make a little pigtail, right? You understand that? And then get you some wire nuts for the right wire gauge and do the same thing on your neutral and the same thing on your ground. It's legal to loop the ground, by the way. It's not legal to loop a hot wire. So when we say it's not legal to loop it, it means I can't come in here and strip it and loop it around and send it out like that. You can't do that. So you've got to break it, right? Does that make sense? So all your parallel is done out in the house. Your parallel is not done at your panel box. It's done out in the house from plug to plug to plug to plug to plug, right? Y'all understand that? But what's nice about a ground fault, if this right here is a ground fault and it says in and out and they're isolated with each other, but everything down below that would be ground fault protected. Every other plug down the line would be ground fault protected. So that way you wouldn't use the pigtails. You would go through the wall. You would go through the ground fault. So normally in your bathroom, your wall, your switch, and your lights are on the same circuit. Well, if you put a ground fault in there, then the whole bathroom would be protected, and every other thing on the circuit. But what a ground fault does, it looks for an unbalance between your hot and your neutral, because all the current out is supposed to be the what? The current coming back. So it's got a little current transformer on there. And as long as those things are equal, the current transformer don't do anything. And if they become unequal, it means that current is going somewhere else, and it's usually going through you or somebody or some way, and it'll kick your ground fault. And sometimes it does. If you got plugs going outside, sometimes the cord gets wet. It'll trip your ground fault because it'll capacity couple into your ground. So those are ground fault circuit breakers. And this is Romax. This is we call this would be 12 gauge. I'm sorry, 12. Two conductors plus a ground. These are, we call these ribbon cables. So each one of these little humps, each one of those little humps is a conductor. And you see why it's called a ribbon cable, because it looks like a little ribbon. What's nice about these is they take up a lot of space, but they take very little vertical space. These are the type of cables we used to run through computers all the time. And then, of course, then we have this cable right here. These are communication cables. This is called a twisted pair cable. Can y'all see why? Because they're in pairs, and the pairs are twisted together. This is networking cable. So this would be the cable we use for Ethernet. Wire Ethernet.
That's what we did in PLC3.
Could be Cat 5 or Cat 6. Cat 6 is new, but most places are in Cat 5. The category determines. So these cables work off of AC. All your signals are AC. These cables are in a loop like this, which means you're creating inductors, right? You understand? So these guys right here, and we're not going to tell you why, but these guys right here have an impedance, an opposition to AC. In a communication system, what we're trying to do is we're trying to get the maximum transfer between our transmitter and our receiver. In a communication system, you get that when all the impedances in your circuit match. So instead of arbitrarily choosing them, we actually set these cables to have a certain impedance at a certain frequency. So this is a network cable, this is a 100 ohm cable, and you can measure with an ohm meter all day long, and you're not going to measure 100 ohms because that 100 ohms is at a frequency. So if you come up here and you run these things, and you untwist those things to make them easy, you just screwed up because you changed the impedance of the cable. I think a 1/4 inch. So this is stranded in solid. So what advantage does solid have? It's easier to terminate because all we can do now, we can twist them together, right? You understand? Tape them down, or in electrical, they use what we call wire nuts, which are basically just insulated nuts that hold the wire together and give it support. The biggest problem we have with solid, where people don't know how to strip that stuff. Yeah. Have you ever? We call them glass cutters, but do they cut glass? What do? They scribe it. So the problem we have with solids, if you get a little nick inside them, you create what we call a scribe. So you'll see these people strip this solid strand wire, and they'll use their knife. They'll turn the blade directly in there, and they'll spin the wire around, and they'll put a little old loop right there. This wire is going to break. And we can see this on our trainers. You'll look at our trainers, especially our old trainers. There's little wires sticking out that we got to dig out because people didn't strip the wires off. Right? Understand that? So on a solid strand wire, if you accidentally put a little scribe in that thing, then that wire's going to break over time. Because it's solid. You scribe it just like glass, right? So this is another advantage of stranded, is that you can nick one and you might lose one strand, but that might not have that one. And we got a chart that shows you how many strands you can effectively lose depending on the number of strands in the cable. So I can nick one of these and I might lose a strand and it will still be okay, right? Understand? This guy, you've only got one wire to work with. This guy, the biggest advantage of this guy is it's very flexible, very easy to run, right? Understand? Very easy to pull through wiring troughs and through conduit like this guy right here. So we got a trough running under the floor right here. There's a trough under there. That's what these holes are for me to pull that cable through there, right? It'd be a heck of a lot easier to pull stranded than it would be to pull solid. Some strands is pretty hard, especially when you get into those big abrasions. Splicing. So splicing, the permanent or semi-permanent joining of two conductors or more conductors together. Termination, attaching the conductor to its final destination point. And then of course we got power cables. And then we got signal cables. And then what we call media or communication. Are we okay? Okay, guys, it'll take about 10 minutes. I'll take it.